How big does a turbocharger's cooling system need to be? I don't know. My name's Ryan, I'm a mechanic in Australia, and we're doing a build at the moment, and we've crossed a fairly unique problem, and I can't find any definitive answers anywhere on the internet. Let's work our way to a solution. So first things first, please excuse the mess. This is the project in question. It's the wife's. It's a pretty cute little thing. I'm starting to really enjoy working on it and building it up. But the problem with this car is when it was made, it was only ever designed to be a town car. It was 500cc, inline, air-cooled 2-cylinder, and it was top speed, I think, was about 80 kilometres an hour. And we're living in country New South Wales. Every road out of here is 100 or 110 kilometres an hour, so it needs to be able to move with traffic. Let me show you the car. So this is the car. This is the engine we're building for it. Couple of things to note. It's got a turbocharger on it, which is going to be a must. It's got an injection throttle body off a motorbike, and a few other little things hiding. It's got a bigger set of pistons and barrels. But the elephant in the room is that's a air-cooled engine, and that's a IHI RHB31 VZ21, which I believe is the world's smallest production turbocharger. And if I can get the camera in there, bear with me. I can't actually see what I'm doing, but that is a water-cooled center. So what we're needing to do, without making too much clutter and mess in the engine bay, is create a cooling system for that little fella. So in essence, the problem we're having here is this is an air-cooled engine with a turbocharger on it. This is nothing new. Two examples off the top of my head where this has been done before are the early Porsche 911 turbos, I believe it was the 930s, and the Kawasaki GPZ 750. That was an inline 4-cylinder air-cooled turbocharged engine, but they had turbochargers that were an air-cooled and oil-cooled center that had no coolant. We're really wanting to get this car working right. We're really wanting to use a turbocharger that was designed for the 650cc car, and lucky for us, there's plenty of Japanese key car solutions. For those who aren't aware, the key car in Japan, it's a small series of car. It's taxed different. It's much cheaper to own and run than a regular sized car, and they do it to encourage people driving small cars, and they are all around the 660, 700cc mark. So what we're needing to do here is make a very basic cooling circuit. So this is a really quick drawing, just a standalone cooling circuit. We're going to have the header tank, which will have our reservoir of coolant in it. We've got the smallest pump I could possibly find. That'll create the flow we require. This representation here, that's our turbo bearing housing. In thermodynamics, that's your Q in, your heat value in to the coolant. Once the coolant's gained this value of heat, it'll keep moving to the radiator in the circuit. This is where we'll get our heat load out of the coolant. So that's our Q out value. And then the circuit will continue around back to the header tank. So extremely simple. What's going to be good about this circuit, which is different to most other turbocharged circuits, with a regular car, it's very, very hard to know your mass flow rate. The cooling system is already in the car. It's doing a number of other things. It's keeping the head cool, keeping the block cool, running the heater core in the car. So the actual amount of coolant passing through the turbocharger is it varies with engine RPM and with other operations that the cooling system is doing at the time. This particular circuit, as long as this pump is getting a constant voltage, the mass flow rate through the circuit will remain constant. Now, The neat thing about that is using thermodynamics, once we have a constant mass flow rate, we can use temperature values to determine enthalpy out minus enthalpy in, and that can give us our heat load in watts. So the unique problem we've got here will be it will allow us to solve this problem very neatly. So we'll see how we go. Component selection. As we have the world's smallest turbocharger, or arguably the world's smallest turbocharger, I thought we should keep the theme going. I like the idea of using OEM parts. I just find that they tend to be well engineered and proven, and if Toyota or Nissan or Mitsubishi is willing to provide a part in a car and offer a warranty, it's usually a very good quality part. So let's see what I've got. This is the water pump I've selected. It's from a Prius. It was on eBay listed as the inverter water pump. So it's quite small. It's weatherproof. It's soft mounted, 20mm inlets and outlets, and that should serve our purpose quite well. Be interesting to see how much current this thing draws. So this is our radiator. It doesn't look that small until you put something next to it. Here's a coffee cup. So it's very, very small. Very small. 80mm by 80mm is for a computer. So no idea how that's going to go. Hopefully it works okay. Got a bunch of copper fittings and copper pipe from Bunnings, which is like our Home Depot here in Australia. And I've got the wife's hairdryer to blow air through the radiator. I'll set up a time lapse and we'll see how we go. So here's the circuit model. We'll start with our pump. We've got a 3/4 inch standpipe here which will simulate our reservoir, holds more water than the system actually needs, and as it gets hotter and it thermally expands, it's got somewhere to move up and down the standpipe. Out of the pump will come along this copper tube, around here to this butane torch. This will be our simulated heat load from the turbocharger. Stating the obvious, it's not a turbocharger. The butane should be burning around about 1400 degrees Celsius, which is far hotter than I would expect the turbo to be. Steel glows red at 460 degrees plus Celsius, and I've never seen a centre housing glow. More importantly, engine oil breaks down at about 115 degrees Celsius. So we're expecting the housing to be maintained below that temperature. But even though this is much hotter than we would expect the heat load to be, it's also got a smaller surface area. So granted, it's not a turbocharger, but it is a heat load, and we're going to be able to see just how well this little pump and this little radiator shed the heat. I gave it a little run before. It started gaining temperature without the blow dryer on. That's our fan for our little radiator. I've got it up to 36 degrees and I've shut it down. The pump is drawing 1.41 amps at 13.3 volt, which is very, very small amount of current, so I'm happy with that also. We've only got a very small alternator in that car. So my next next part of this plan, I suppose, will, while this is running, it's moving the water around at 3 litres per minute. I calculated that before while we were doing the time lapse, and I made a mess everywhere. So I only took one measurement. It's crude, but that'll do. 3 litres per minute, and with water, that's 3 kilos per minute as mass flow. So we'll fire up the butane and we'll get it to 80 degrees Celsius. I've got a K-type thermocouple on a fluke here after the heat load, immediately after, because this is the most important, this will be the hottest part of the circuit. We don't want to boil, no localised boiling if we can avoid it, so this is probably the most critical temperature we'll be dealing with. And we'll want to be able to keep it below 115, preferably below 105 or 100 even. And as this here isn't pressurised, as soon as we get to localised 100 degrees, we'll start blowing water out the standpipe. So here we go. Actually no, we'll set up a stopwatch. "13 minutes 50 seconds, we have hit 80 degrees Celsius, which is what I consider to be the operating temperature of an engine or cooling system. What we'll do now, keep the pump running, keep the heat source on. We're going to put the hairdryer onto its lowest setting to provide some airflow through our Baby 8 radiator. So far it's had coolant going through it but no air, so it's not really been doing much at all. So we'll get that kicked off. And we'll see how the temperature reacts. It's the next day. We've been kicked out of the kitchen. Here we are in my study. Welcome. Yesterday wasn't a complete loss, but it did surprise me. The radiator was far more efficient than I was expecting. I have done a graph. We'll have a look at that. Bring that up. So the graph shows two distinct regions. You've got a fairly steady rate climb while the pump's on, the heat load's on, and the radiator is in the circuit, but there is no fan on. It rises quite quickly to operating temperature. I chose to use the hairdryer because I had a number of different fan speeds I could use, but even on the lowest fan speed setting, the radiator and fan combination was so efficient that it pulled too much temperature out and was approaching equilibrium around the 40 degree mark, which is lower than what I would consider desirable. So what do we do now? We've got to make it less efficient. It's the smallest radiator I can find. It's the smallest pump I can find. So we're going to have to find a smaller fan. See how we go.